Hi everyone. When we compute some quantity using mathematical models with the help of a computer, we will always see some discrepancy between the actual value and the value achieved by our computation. This discrepancy is called the error. There are various types of errors of different nature. Some error is due to the idealized hypothesis that we have assumed for the model, which in general will not hold in reality. This is the modeling error. Some error is due to the limited resolution of the measuring tool that we used, no matter if it is a ruler, a scale, or a thermometer. We will not be able to draw meaningful claim beyond the smallest division of the equipment. This is known as the measurement error. Also, since we are using the computers, some error arise due to the way our computer saves and operates data. There are two subcategories in large. The first one is called the round-off error, which is due to the floating point arithmetic. The second is called the truncation error, which is due to our attempt to approximate some infinite quantity using finite materials. In reality, errors of different nature may interact with one another along the process of our computation. To illustrate the idea, let us look at a simple pendulum, which consists of a point mass attached by a rigid massless rod and moves under gravity. The movement is governed by the Newtonian law, which is described by the following ordinary differential equation. Here, x is the angular displacement of the rod from the vertical, L is the length of the rod, and g is the gravity constant. Assume that we want to simulate the trajectory of the pendulum using numerical methods. Then we will probably have to deal with all aforementioned types of errors. To begin with, there will be some modeling error. For example, this model assumes that the rod is rigid and massless. It assumes that the pivot has no friction and there is no air resistance. All these assumptions are not true in our real life. Second, to solve this equation, we need to know the length of the rod, and we need to use some equipment to measure this length. However, we will not be able to measure precisely the length of the rod, no matter which ruler we're going to use. This is the measurement error. Last but not least, we will need to solve this equation by the computer. First, we need to evaluate the function sin x. Let's say the amplitude of x is small. Then sin x is roughly speaking just x, and we will try to use x to approximate sin x. It is not perfect. If we want to be more precise, we can add in terms of higher orders in its Taylor series, but no matter how many terms we're going to take with us, we can only take finitely many terms. So by the end of the day, we will evaluate sin x using a polynomial, which is not sin x itself. Moreover, in our scheme, we will use finite difference to represent the derivative, although when the small displacement delta x is small enough. This is pretty close in theory to the true derivative. It is not the true derivative, and there is always an error due to this discretization. Last but not least, even if your model is perfect, your measurement is perfect, and these functions and derivatives are computed in a perfect scheme, still there will be an error. That is because our computer does not really know what is a real number. It can only deal with floating point of finite precision. And these round-off errors will also be very important. In the scope of numerical analysis, we will focus mainly on numerical errors, that is, the round-off error and the truncation error. These errors might also twist with each other. For example, when we are computing the derivatives using the finite difference, not only does the truncation error involve, since the finite difference involves subtraction and division, the round-off error due to finite precision arithmetic will also get involved, and figuring out which part is the major source of error can sometimes be very challenging. Alright, now you have seen the error analysis in a nutshell. In the coming section, we will discuss the absolute and relative error.